theoretical researcher while they're here. In this case, it's Zweibel. Also interacts informally with the postdoctoral fellows and graduate students at CITA. And so Ellen's been talking to a lot of people in the last couple of days, and I hope she's been enjoying herself. Certainly, we've had a lot of time, a lot of fun talking to her and learning a lot. And the visit is intended to be the highlight of our year, and this year certainly has been that. So this is, I think, the 18th Sackler lecture. And as I said, the lecturer is Ellen Zweibel. She's the WL, I'm not quite sure how to say this, Kraushaar, Professor of Astronomy and Physics. And she's the chair of the Department of Astronomy at the University of Wisconsin-Madison. She did her undergraduate work in mathematics at the University of Chicago and graduate work in astrophysics at Princeton University. She worked with Landon Spitzer and Russell Coldrew while at Princeton. These are, if you're familiar with astronomy, very well-known names. After a stint at, it wasn't right immediately after you went to Berkeley, is that right? Then you went to the Institute in Colorado, okay. So the Institute for Advanced Study. And then she went to a professorship at the University of Colorado, and she was there from 1980, I guess, until 2003, when she moved to Madison. She's written more than 150 scientific articles. Her emphasis has been mostly on plasma physics-related problems, but her thesis I was interested to read was on cold stellar disks. So she has a background in dynamics, and in plasma physics, where she's written papers on a number of topics to do with star and galaxy formation and the physics of the interstellar medium. Lately, she's been putting a lot of attention into cosmic rays, so that's the topic of her public lecture tonight. As you can see from the title there, the fastest particles in the universe. So with that, I'd like to welcome Ellen.
Can everybody hear me?
Yep.
Thanks very much, Norm. It's the highlight of my year. I always love to visit CITA. There's groundbreaking research done here. The University of Toronto, as I'm sure you all know, is one of the world's great universities. I think Toronto is one of the world's greatest cities. So I love being here. Thanks for the opportunity. So the subject of the fastest particles in the universe started very slowly. Yeah, please. So it started slowly with the observation. Where's the with the observation in 1785 that air is partially that cosmic rays arrive preferentially from the west. And what that implies is that they're responding to the magnetic field of the Earth. So the Earth has a magnetic field, kind of like the magnetic field of a bar magnet, and charged particles run in little spirals along these field lines, and positively and negatively charged particles go in opposite directions. And so this preferential arrival from the west was consistent with the cosmic rays being positively charged particles and not light. So particles with a low energy, so the size of the orbit that a particle makes around the magnetic field line depends on the strength of the magnetic field. And low energy particles get trapped in the Earth's radiation belt. So these are the Van Allen belts. They were discovered in the late 1950s. But a particle with a very high energy will just kind of not see the Earth's magnetic field at all. It'll just kind of come in like this. And that's what the cosmic rays that arrive at the surface of the Earth are doing. So then, we still didn't know very much about the origin of these particles. And I'd like to read to you this kind of poetic query that actually comes from a Popular Mechanics magazine in 1932. Cosmic rays, only thing immortal. Neither stars nor worlds, sunlight or heavens, can science admit to be eternal. Only one thing known to science can be called immortal, the cosmic rays, investigated, among others, by the famous California physicist Dr. R.A. Millikan, who's actually also a great publicist as well as a great physicist. These rays may even be relics of days before there existed any universe as we know it now. So cosmic rays really kind of inspired the popular imagination. But in 1948, Phyllis Fryer, who was then a graduate student at UCLA, showed that cosmic rays contain many different kinds of atomic nuclei, most of them not created in the Big Bang, created later in stars. So that suggested that cosmic rays have a more contemporary origin. And there had been a theory for this, proposed in 1934 by Walter Baade and Fritz Zwicky. And they proposed that cosmic rays originate in supernovae. And so here's a famous so-called supernova remnant. I'll show you an image later taken with X-rays of what's inside this remnant. This is the Crab Nebula. It was first observed by Chinese astronomers in 1066. That's when the supernova went off. So it's a little more than 1,000 years old, was once a star. Now it's this fantastic-looking nebula. And Baade and Zwicky said, well, here are these very high-energy cosmic rays. Maybe they come from very high-energy explosions, namely supernovae. So then, in the early 1950s, it was discovered that our entire galaxy has a magnetic field. So just as the Earth has a magnetic field, our galaxy has a magnetic field. And here it's revealed by the polarization of starlight. So let me parse this picture for you. So first of all, it's a negative. So the stars show up in black, and the sky shows up in white. And these lines here trace the magnetic field of the galaxy similar to the way iron filings trace the poles of a magnet. So this is caused by little tiny grains of dust in the interstellar medium. That's what makes the Milky Way kind of look patchy and blotchy. And it turns out that these little dust grains are lined up by the magnetic field, and that causes them to polarize light that comes through it and reveals which way the magnetic field points. So by the early 1950s, the big pieces for cosmic ray research were in place. So we knew that cosmic rays, known since the time of Coulomb in 1785, high energy positive ions, so atoms with electrons missing, that strike the Earth from space. They're truly cosmic. They're vacuum that we can achieve on Earth, but there is some gas there. And 1 in a billion particles in interstellar space is a cosmic ray, and it moves at near the speed of light. So these cosmic rays, because they're moving so fast, have as much energy as the energy in the rest of the gas. So 1/1,000,000,000th of the particles in the interstellar space, the space between the stars, have as much energy as all the rest. And if that happens suddenly in this room, the temperature would drop by about a half, so now it's about 20 C, it would drop down to 10 C. That would be noticeable. And 1/1000,000th of the molecules would become lethal radiation, zipping around and able to do damage. Now, this is nothing to worry about. We know this never happened, right? It just never happens that spontaneously almost all the particles give up their energy to 1/1,000,000,000 of them. It's not like money. But it does manage to happen somehow in interstellar space. So with all the pieces in place, there was kind of a golden age of cosmic ray discovery. But teasing information out of that to make this a golden age was very hard to do. So an important technique at that time, and still used today, is particle tracks in photographic emulsions, or something equivalent to photographic emulsions. And this is the kind of track that two different particles leave, a light nucleus and a heavy nucleus. And here is a bunch more tracks in a little track of plastic. So this technique of studying energetic particles, so this is used in high energy laboratory physics as well as cosmic ray physics, was pioneered by Marietta Lau, who has this biography written by her, and figuring out kind of how to make sense of all the statistics, what's significant, what's just an accident, one of these things. But there are about 35 million people in Canada, so that works out to about 3 Canadians a year hit with something like this. But fortunately, these particles break up in the atmosphere of the Earth. This is a schematic of cosmic ray coming in and shattering into this whole shower, the so-called extensive air shower of subatomic particles. And this actually is the key to how we observe these highest energy deep galactic disk. There's a supermassive, probably about 1 billion solar mass black hole at the center of this galaxy, far too small to be seen. And it's created these enormous jets of hot ionized material that also contain cosmic rays. So in addition to these visible jets, could galaxies of this type be spewing out these ultra-high energy cosmic rays? Well, unfortunately, or as it happens, there's no statistical association between positions of where the cosmic rays come from and the positions of these active galaxies on the sky. So yes, you can say there's a little cluster here. Turns out not to be statistically significant, according to our best ideas about statistics. So we need another idea. But before I tell you that idea, I want to tell you one more clue, which is that cosmic rays, particularly of the highest energies, collide with light and are destroyed by ordinary light. And this was first pointed out independently by these three guys, Bryson, Kutzman, and Sackler. And it's called GZK. And here's a schematic of what happens. So in comes proton, and in comes a photon, a little particle of light, and they interact, and the proton goes out with less energy than it had before, and there's no photon anymore, there's a pi meson, which decays. And so a very high energy proton will go through a whole series of these interactions on its way to us, and it'll become progressively degraded in energy. And the higher the energy it starts with, the more degraded it will come. It just busts up. And what this tells us is that these ultra-high energy cosmic rays must be produced, sorry, that's T, within about 150 million light years. And this sounds like a lot, I know, but it's actually just a small part of the visible universe. So this tells us that these ultra-high energy cosmic rays, although they're probably not produced within the galaxy, are produced within our kind of immediate galactic neighborhood. Okay, so let's try another source. Let's try pulsars. So here's the same image of the Crab Nebula, the supernova remnant, and here's an X-ray image showing that at the center of this remnant, there's this pulsar, which we think is a so-called neutron star. So a neutron star has about the same mass as our sun, but it's only about 10 kilometers in radius. It's an extremely dense, primarily neutron ball with this super strong magnetic field, and it spins very fast, maybe 30 or so times a second in the case of the Crab pulsar. And these are formed in supernova explosions. This is what's left behind when most of the exploding stars explode. There's a kind of special class of pulsar called a Magnetar. And the study of magnetars was pioneered by a CITA professor, Chris Thompson, shown here. I don't know if this describes magnetars, but here he is. And a magnetar, so here's a schematic of a magnetar. Again, this is an artist's conception. So here are its magnetic field lines, and this kind of crazy-looking pattern here, like if you dropped, heated up a marble and dropped it in cold water, shows the crust of this neutron star cracking under the stress of its magnetic field. It has such a strong magnetic field that the magnetic field breaks the crust. And this is an explosive event that releases a lot of energy, and this might be the energy source of these very high energy particles. So the advantages of the magnetar model are we have super strong magnetic and electric fields.
just a question. What's the source of magnetic field in these from galaxies?
Oh, that's, so we were debating that today. So, we don't think the magnetic field was created in the Big Bang. There are some good reasons for that. There might have been an exotic process, for example, during cosmic inflation, that created a very weak magnetic field that pervades the universe. There are also ways, using ordinary plasma physics, of making magnetic fields from nothing in objects like stars. And so, one way or another, these first so-called seed magnetic fields were made, and then they were amplified by being dragged around by things like the rotation of the galaxy, the turbulence of the galaxy, rotation of the star, turbulence of the star. So that seems to be where they come from. But it's, in many ways, an open question. It's one of the great unsolved problems in cosmology.
Thank you.
There's another question here.
Yeah, so I'm a layperson in all of this, and I think I have a simple question, but I don't know what the connection is. Every few years, I hear something about the sun throwing off the plasma or something, and then a few days later, northern lights, and then everybody's worried it's going to screw up our electronic stuff. Is there any connection with that and what you're talking about?
So the sun is, so these particles, they can screw up our electromagnetic emission, and the most energetic solar flare ever recorded put out so much energy that telegraph paper caught fire, okay? So the sun, every few hundred years, the sun didn't do this. This was called the Carrington event. But the energies of these particles are lower than the kinds of energies that we're talking about. However, the sun is a wonderful laboratory for studying the kinds of processes that can create high energy particles. So we see that what seems to happen on the sun is that energy in the magnetic field, which we see in sunspots, is converted to these high energy particles. And then some of them escape, so some of them just are buried in the solar atmosphere, but some of them escape, and whole blobs of plasma come and they make their way to us. And you're very lucky to be able to see the northern lights.
What's known about the composition of the ultra-high energy cosmic rays?
So, they are most likely either protons or iron, okay? And that's an inference. So, we're really, in some ways, we're really on our own in interpreting these things because there's such a huge gap between the energies that we can create in terrestrial accelerators and the highest energy particles that come to Earth. So we think we know what a nucleus looks like at those energies, but it's, there's a certain amount of extrapolation and guesswork involved. So the idea that they're protons or iron comes from ideas about this so-called GZK process, that the fact that we can see particles of the energies that we do seems to sort of narrow it down to protons or iron. But there's probably some room for other.
Would either of those fit better with the Magnetar neutron star crust source?
I don't know, actually. I don't know kind of what the very outer crust of one of these young objects would look like. Then there's also the environment right around the star. I'm not sure, but it's something else.
I'm a layperson too. I do construction for a living. The two things you showed us in Argentina, I forget how many water tanks, but they're
Yep.
spread over 6,000 square miles or 3,000?
3,000 square kilometers.
Big area.
Yeah.
And the observatory that you call Ice Cube in the South Pole.
Yeah.
Okay, nothing gets done in the South Pole that isn't a big logistical problem.
Oh, yeah.
Especially if you're talking about thousands of strings dangling a kilometer below the ice, okay? With all the problems that the human race is facing on the planet today, how are these things going to help us? The knowledge that you're gaining, what are we going to get out of it?
So that's a really
clearance to write the check for Ice Cube, right? And you've got to make a proposal to somebody somewhere. Like
Yeah.
that looks like a heavy operation. I mean,
It's
just
the
getting that-
national, so in the United States, it's the National Science Foundation. And, you know, it's very, I find it hard to kind of measure the effects of all these things. So among other things, so Ice Cube has trained a lot of students, undergraduate students and graduate students, and some of them are continuing to work on this type of thing, but they fanned out everywhere. There are people working in medical physics, there are people working in software, in computing, people making detectors. One of my former colleagues who, so originally he invented an X-ray telescope. Okay, so that's extremely expensive. That would fly there from space. This big X-ray telescope. Then he teamed up with some physicians and he used the same technology to create for mammography to detect breast cancer. So there are spin-offs. I mean, it's very easy because sometimes people say, oh, the space program was worth it because we invented TAN. I'm not going to tell you that, but I know it's true. But I don't think that's a justification. But it does leave a big footprint, I think, in other areas of society.
That's the surrounding things that happen. But at some point, when someone was proposing Ice Cube, there's something very specific that you want to know from the results of that experiment. You know, and when you get the results, what's the missing piece you're looking for, and what's the puzzle you're trying to complete?
So, so these neutrinos, Ice Cube was originally developed to detect neutrinos. And neutrinos, because they don't have any electric charge, are completely non-influenced by magnetic fields or anything else. They really come directly from the source. And so, if we can see the neutrinos, we'll see these sources of the highest energy particles in the universe. If they hold the key to the dark matter, so you know only about 4% of the universe is sort of ordinary matter, the kind of matter that we are, 25% dark matter, 70% dark energy. I don't know. I think, you know, we've always tried to find what the world is made of. And this continues on that path.
Can I answer that question too?
Thank you for a sparkling introduction. Again, outside my universe of discourse, there's a talk on Friday, I believe, about another research endeavor at the South Pole looking for gravity waves or twists on gravity waves. Are they in any way connected with your endeavors?
There are some connections at a deep level. So if these gravity waves from inflation are detected, if we can learn something about this inflation process, which seems to have a lot to do with the nature of the universe we live in, we may know where the magnetic fields come from, and we may know what the so-called dark matter is.
And do they occupy some other research facility next to yours, or the Ice Cube?
I actually don't know exactly where. Does anybody else here know?
I think BICEP's right next door.
Louisiana.
Well, no.
No, this is-
BICEP is the experiment he was describing down the South Pole. It's actually attached to that same complex.
Is that right?
And curiously enough, the talk on Friday is not just going to describe something based at the South Pole, but going back to the origins of seeing cosmic rays in HAST. One of the major experiments that we have a big involvement here at the University of Toronto was associated with a balloon that went up to the top of the atmosphere and was looking for gravity waves that way. So it is intimately related to this problem. It's just that the energy of those waves is much, much smaller than what is being talked about here, even though it's the ultra early universe where the energies are unimaginably high.
So that experiment's also run out of the South Pole. Much of things from the South Pole, because you can keep them up in the air for weeks at a time, they'll circulate
cosmic waves? Has it been, since the Big Bang, has it been decreasing, or is it constant, has it been the same?
So by looking at lunar samples and ice cores, we can say something about the rate at which cosmic rays have struck the Earth over time. And it seems to have been about the same for maybe as much as 100 million years. So this really seems to be kind of a universal phenomenon in our galaxy.
On the other hand, that's only 100 million out of
Yeah,
10 billion years.
that's what I'm saying, yeah, that,
Okay,
Going back to
all right,
Big
in that
Bang.
case,
Yeah.
so we can see evidence for cosmic rays in galaxies that already existed when the universe was just a few 100,000 years old.
okay.
So,
But we don't know about whether it's been constant all the way back until.
So, that very kind of exhausted-looking young lady in front of the blackboard, my graduate student, Toby Yost-Hull, she has been studying the gamma rays and radio waves produced by cosmic rays in other galaxies. And it was a surprise to me, but although these galaxies that we looked at are all actually very different from our own, if you make the same assumptions about cosmic rays, that they come from supernovae, and so on, we can model what they look like in radio and gamma rays. So these processes seem to be universal in many galaxies.
Okay. That's a comforting thought. The laws of physics actually hold me.
Yeah.